Hello. We are going to make a short video on a couple examples of word problems. If you were in class the other day, then you would have seen that we did this example problem. But I did want to take one more problem. One of the LAs recommended that I take a look at number 6. So let's take a look at this problem here, number 6. And it's very similar to the example that we did in class. Just some of the stuff is slightly changed. So one of the formulas that we'll need is this distance equals rate times time formula, and that'll come up later in the problem. So just kind of keep that in the back of your mind. And so now let's go ahead and read the problem, and we'll try to organize all of our information into a table, and then we'll see what we can do from there. Okay, so it says, at a cross-country track meet, Alicia ran 8 miles per hour for the first part of the race, then increased her speed to 12 miles per hour for the second part. If the race was 21 miles long and Alicia finished in 2 hours, how far did she run at the faster pace? So the question is, how far did she run at the faster pace? Okay, so there's multiple ways to do this problem. Whatever seems most natural to you is the method that you can use. Personally, let me go ahead and set up my table here. I did it a couple different ways, and you get the answer. You get the same answer no matter how you do it, assuming that you're setting things up correctly, in one of the correct ways. And so let's go ahead and take a look. So we're dealing with distance, rate, and time. So I like to organize my information in a table, DRT. Now we have multiple sections of the race, 2 sections. And so let's call it the first part and then the second part of the race. And then I'll put a total row at the bottom, just in case it comes in handy. In some problems, it might not, but we might need it. Okay, so what do we know? Let's just start by reading the problem, in order. It says, Alicia ran 8 miles per hour for the first part of the race. So that is a rate for the first part of the race. And these are all in miles per hour. Times are going to be given in hours, and distances should be given in miles, so everything stays consistent. Okay, then she increased her speed to 12 miles per hour for the second part. So in the second part, she ran 12 miles per hour. The race was 21 miles long, so that's a total there for the entire distance. That's in miles. And Alicia finished in 2 hours. So the total time is 2 hours there. Okay. And it doesn't look like, now we want to know how far she ran at the faster pace. And so we could, if we wanted to, define our x, our variable, our unknown, to be how far she ran at the faster pace, which would be this, box here. But I'm not going to do that because there was a little bit of confusion as to whether you could define the variable to be somewhere else. So I'm going to let x be the amount of time she ran at the faster pace. And then if we know systems of equations, we can use a second variable. Let's let y be the amount of time she ran at a slower pace, or the first part. And so now we go back to our equation, distance equals rate times time. So the distance that she ran in the first part was she ran 8 miles per hour for y hours. So she would have run 8 times y miles. Then the second part similarly will be 12x miles. And now we know that the race was 21 miles long. So the distance of the first part plus the distance of the second part is equal to the total distance. So the distance of the first part was, we have an expression for that, that's 8y. The distance of the second part is 12x, and the total distance is 21 miles. So we have an equation here. It has two variables, so we need one more equation to be able to solve this. But there is another equation kind of embedded in here. The time spent on first part, I'll just abbreviate here, the time on the first part plus the time on the second part is equal to the total time. Since there were only two parts, these two sum together. The time on the first part, we said that is y. The time on the second part is x, and the total time was 2 hours. And so now we can use these two equations, right? This is very important here. If you remember from systems of equations, once you have two equations and two unknowns, you can use the substitution method to solve. Now, okay, so let's continue here. We'll use substitution. So I'm going to subtract the x to the other side. And so I get y equals 2 minus x. Now I can take this y, or y is equal to 2 minus x. So I'm going to go ahead and plug that in for y right there. And so I get 8 times y, which is now 2 minus x. If I distribute, I get 16 minus 8x plus 12x equals 21. And then combine like terms, the negative 8 and the 12 give us positive 4. And subtracting 16 on both sides gives us 5. And then dividing by 4 on both sides gives us x is equal to 5/4. And so this is where the confusion kind of came. Some students said, well, is this our answer? And we need to look carefully at what x is. According to the box where we defined x, x is the amount of time spent on the second part. So this is 5/4. If you divide this, this is 1.25 hours spent on the second part. Is that what we wanted to answer this question? Did we want the number of hours? No, it says how far did she run at the faster pace? And so how far she ran at the faster pace is given by the expression in this column here, the distance for the second part where these two overlap, that is the expression 12x. So now all we need to do is plug in our x into the expression 12x, and that will be our answer. So the distance for the second part is equal to 12x. Well, x we know is 5/4. 4 goes into 12 3 times. And so this is 15. Now this is a distance, so this is in miles. So how far did she run at the faster pace? She ran 15 miles. At the faster pace. Okay, so it's a nice way to do this problem. There are other ways, that you could do this, but here's one way. And we essentially avoided fractions, throughout the problem-solving process until we, finally solved for x. You could have defined x to be here, or x to be here, as we said, or x to be here, and then continued from there, defining y to be something else. It really depends on how you want to define it. Excuse me. Okay, so yeah, so it's a good idea to, when working on these problems in class, to try maybe define things the same as your partners in your group. And if you do define things differently, that's fine too. If you choose to go that way, just know that at the end, your answer should match, in the sense that I got 15 miles as the answer for the final, for the question that was given. So if you don't get 50 miles, if you get x equals 5/4, well, maybe since you define things differently, maybe your x, if you define things differently, it means something different. And so you need to figure out, well, how do I get this to become, how do I use this to get the answer to the question? Okay, good. Cool. Now, one more problem that I wanted to do is one of these mixture problems. So we did an example of distance, rate, and time. We didn't have we didn't have enough time to do one more question on mixture problems. So we're going to take a look at this problem here. And before we do this problem here, let's take a look at a similar idea, but using, I'll just make something up here. Using, let's use orange juice, right? Something that's a little bit more easy to understand, and we'll use simpler numbers than 6% and 20%. But imagine that you had let's say 6 liters of 100% orange juice, right? So it's freshly squeezed, you squeezed it from oranges. This is what we consider to be 100% orange juice, right? You just squeezed out 6 liters from oranges of orange juice. And then we also have next to it, let's say another 6 liters of 0% orange juice. And let's say that this is water, right? It's actually just pure water. So we'll call it 0% orange juice because here we're trying to, we're going to end up trying to figure out how much or what percent concentration of orange juice do we have when we mix some quantity of each of these into another bucket. All right, so here's a third bucket, and I'm going to mix. And let's just suppose that this is a bigger bucket. And so I'm going to mix, let's say, all of this, 6 liters, and all of these 6 liters. I'm going to mix them into this third bucket. And so, first of all, how much fluid am I going to have in this third bucket? I could call it X liters, right? Some amount. But we can see that if we mix these two liquids, then it's just going to be 6 liters plus 6 liters, right? We just add the amounts that we mixed. Whatever amount we mixed of each type, that's what we're going to get in the mixture. And so this will give me, I'll put 6 plus 6, which is 12 liters. Okay. So this is 12 liters. Now, what is the concentration of this new mixture? Let's go ahead and organize this information into a table. Now, of course, these numbers are easy because I made them that way. So I'm trying to make an easy question here so that we can understand the idea. And then we're going to, jump into one that's a little bit more complicated. And so in this case, what are our rows and columns? We'll call it, the mixture 1. And I'll put a big 1 here. So this is mixture 1, a 2 here, mixture 2. And then the, I'll call it final solution. Solution in the sense that this is a mixture, a final mixture, if you want to call it. Okay, so what are the relevant quantities? Well, we want on, what do we call them here? Let's call them the total amount of mixture. The concentration. And then the amount of pure orange juice is going to be something that's relevant. So the amount of the total mixture, let's say for mixture one, that is that is 6 liters. This is going to be in liters. The concentration is going to be a percentage, but we really should write it as a decimal. So for mixture one, this is going to be 100%. And I'll write both of the numbers here, but I'll only use one. This is the percentage, and then the decimal is just 1.00 or 1. So how much pure orange juice is inside of this first mixture? I could multiply the total amount of mixture. If I multiply the total amount of mixture by the concentration, then this gives me the amount of pure, substance, of pure orange juice in that mixture. So, okay, this one's an easy one because it's 100% orange juice. If there are 6 liters of the mixture, let's say, and it's 100% orange juice, then how much pure orange juice is in there? 6 times 1, we just multiply straight across. 6 times 1 is 6. This is also going to be in liters. Okay. The mixture number 2, there's also 6 liters. This one is 0%, which as a decimal is still 0. 0% orange juice. So how much pure orange juice is in mixture number 2? Well, we multiply across. 6 times 0 is 0. Okay, and then for the final solution, we're mixing 2 of them together. So I'll call this your final solution. How much total liquid is going to be in there if we mix the 6 liters and the 6 liters? Well, this is going to be 6 plus 6, right? We just add down the amounts, and this, I'm going to put a big 12 there. The concentrations, we can't really add those up, but the amount of pure orange juice, remember, if there are 6 liters of orange juice in here and 0 liters of orange juice, when we mix those two together, well, how much pure orange juice is going to be in the mixture? Well, it's going to be 6 liters from one bucket and 0 from the other. So a total of, we'll add here too, 6 liters of pure orange juice in this 12 liters of total mixture. Okay, so I'm going to focus here for a moment. In the final solution, we have 12 liters of liquid, and 6 of those liters are pure orange juice. So what is the concentration of that new liquid? It's no longer 100% orange juice or 0% orange juice. It's going to be somewhere in between, right? Because there's 12 liters of mixture, but it's not 12 liters of orange juice, and it's not 0 liters of orange juice. It's somewhere in between. And so we can actually use this same formula here that I have down below and plug in our numbers. So there's 12 liters in the total, 12 total liters of mixture. The concentration right now, we don't know what it is, so we'll put times X is equal to the amount of pure orange juice. The amount of pure orange juice is 6 liters. And if we divide by 12 on both sides, this is now an equation here that we can solve. X is equal to 6 over 12, which reduces to 1 over 2, 1/2, or 0.5 as a decimal, or 50%. And I think hopefully, that was pretty clear that that was going to be a 50% mixture in this case, because we added equal quantities, 6 liters and 6 liters of 100% and 0%. What's going to be, in between 0 and 100? That's 50%. So actually, let me delete that 50. Yeah, that 50% is going to go in there. And we calculated that. Okay, so hopefully that example wasn't too hard to understand. It was made to be simple in a sense, so that we could understand the idea. And we're going to use this kind of idea here in this problem, where it's a little bit more, the numbers are a little bit more complicated. But let's go ahead and try this problem here. Okay, so we should read the problem. Let me bump this over here. You know what? Actually, I'll do it side by side. Let's see if this comes out nice. Okay, so a nasal decongestion. As a nasal decongestant, doctors sometimes prescribe saline solutions with a concentration between 6% and 20%. In the old days, pharmacists had to create different mixtures, but only needed to stock these concentrations since any percentage in between could be obtained using a mixture. An order comes in for a 15% solution. How many milliliters of the 20% solution must be mixed in with 10 milliliters of the 6% solution to obtain the desired 15% solution? Okay, well, there's a lot going on there. So let's go ahead and try to draw a picture. So, and these are, in this case, well, let's see. So there is a 6% solution, 20% solution, and we want a 15% solution. Okay. So far we've used the fact that there is a 6%, 20%, and an order comes in for 15% solution. So that's our final, concentration that we want. How many milliliters? So how many milliliters of the 20% solution? So we don't know how many milliliters should be mixed in of the 20% solution with 10 milliliters of the 6% solution. So we know we're going to mix in 10 milliliters of the 6% solution, and we want to obtain the desired 15%. Okay, so here's that's a picture essentially of what we're doing, and we're going to mix these two liquids in here. Now, I really like the tables, so let me draw a table, and then we'll fill it in. Okay, so let's do our little rectangle here. So we had earlier a total amount of mix. So total amount of, I'll call it a mixture just to keep it consistent with the previous example, but mixture, solution, whatever you want to call it, concentration. And I believe on the worksheet, there's actually a suggested kind of naming. Yeah, I don't have it up right now, but there's suggested naming scheme here, and I can actually go to it. Oops, wrong worksheet. Here we have, in an alcohol solution, the volume of pure alcohol is equal to the total volume of the solution multiplied by the percent concentration, right? So this is talking about alcohol because that's what the the problem here is talking about alcohol, but ours is talking about a saline solution. So the volume of, notice that we're looking at the amount of pure substance, alcohol, and then the total amount of the solution. In this case, they're talking about volume, but it's total amount of a solution, and then multiplied by the percent concentration. So that's essentially what we're working with here. The total amount of the mixture is going to be the total amount of the mixture times the concentration is going to give us the total amount of pure, and then in the saline solution, we're interested in the amount of pure salt. All right, so saline solution is made with some sort of salt mixed in with a liquid. Okay, so those are our quantities of interest. What are the different categories here? Well, we have our 6% solution, if you want to call it like solution one or mix one, whatever you want to call that. I'll call it, yeah, I'll also put mix one. And then mix two, mixture two, solution two, that's 20%. And then the final mix or final solution. Okay, so let's go ahead and fill in the table. The concentration is the easiest one to fill in for this one here, because 6% as a decimal is 0.06. 20% is 0.20. And then the final solution, 0.15. Let's see here. Which other quantity do we know? We know 10 milliliters of the 6% is being mixed in. So 10. So in those 10 milliliters of 6% saline solution, how much pure salt is in that, right? Because imagine 10 milliliters. That's, a good amount of liquid here, in our picture, but only 6%, only very little. Why? Yeah, what does that 6% mean, right? Going back to our orange juice example, 100% of it is orange juice. That means all of it is orange juice. But if we have 10 milliliters of a solution and only 6% of it, very small amount, is well, that's the concentration, 6%. Then 6% of the 10 milliliters is the salt. And so if we multiply 10 by 0.06, we get 0.6 milliliters of pure salt. Very small amount. Not even 1 milliliter. Okay. Next. Our 20% solution. See, yeah, that's what we don't know, right? It says the question was how much or how many milliliters. Let's see, I'll do this in red. How many milliliters of the 20% solution must be mixed? So that's what we don't know. And so that's this quantity here. So I'll just put an X there. See if I can make it visible. But what we do know is if I mix those X milliliters of 20% solution, I can find the total amount of pure salt in that solution by multiplying 0.20 times X. Just multiply straight across. Now, what else do we know? How much liquid, how many milliliters are going to be in this mixture? Well, you can see it from the picture. If I mix 10 milliliters and X milliliters into a third bucket, then I'm going to have 10 plus X milliliters of the final solution. And then looking at the total amount of pure salt in that final solution, well, we would multiply 10 plus x times its concentration, 0.15. So this is going to be 10 plus x times 0.15. And now one thing that I did not mention in the previous example, which we can mention right now, is very simple, is that the amount of pure orange juice in the first solution plus the amount of pure orange juice in the second solution is going to be equal to the total amount of pure orange juice in the final mix. Right? And you can see that in this right-hand column here, in the amounts of pure orange juice. If there are 6 liters of pure orange juice in the first solution, no pure orange juice in the second solution, when you mix those two up, sure, there's going to be a mixture. It's no longer going to be 100% orange juice. It's all going to be mixed up. But in that mixture, floating around in that 12, the 12 liters of final solution is going to be those 6 liters of pure orange juice are still going to be kind of floating around in there. So the total amount of pure orange juice in the final mixture is going to be 6 plus 0. And so we can use a similar idea here. The amount of pure salt in the mixture should be, or is going to be, just the sum of the amount of pure salt in the first 2 mixtures. So the amount of pure salt in the, mix 1 the amount of pure salt in mix 2, that's going to be equal to the, amount of pure salt in the final solution. Okay, and so we have expressions for all of these quantities. This is 0.6. This is 0.20x. And this is 10 plus x times 0.15. And now we can solve this equation here. This was kind of like from day 1, solving equations. We can multiply by 100. That's going to move the decimal place over 2 places in all of these numbers. So we go 1, 2 places. That gives us 60. If we move this 2 place, 20x. And here's going to give us 15. So 60 plus 20x is equal to 10 plus x times 15. And now we can just solve this for x. We have no decimals. That's nice. So we have 60 plus 20x is equal to 150 plus 15x. If we subtract the 15x to the, I'll write it down here, onto the other side, on both sides, subtract 15x. At the same time, we can subtract 60. And so we get 5x equals 90. And if we divide by 5, x is equal to 18. Now, what is x? If we go back to our problem here, we defined x to be the total amount of the second mixture. The total amount of the second mixture. And that's exactly what we wanted, right? How many, in red there up on the word problem, how many milliliters of the 20% solution, that second mixture, must be mixed with those 10 milliliters? And we've found that 18 milliliters of the 20% solution must be mixed with 10 milliliters of the 6% solution to get the desired 15% solution. All right. So let's go ahead and check our answer. Actually, this is the answer here. We're done now. But just for one quick minute here, we can check the answer and see if this is actually correct. Would this actually get us a 15% solution? And let's see, should I just fill it in up here? Or should I do it with the box? Yeah, I'll fill it in up here, in the picture, and then we can do a little calculation. Okay, so we'll put this here. This is, we found that the answer X is 18, so that we're going to mix 18 milliliters. And so notice that if we mix 18 milliliters with 10 milliliters, now we're going to get a total of 28 milliliters in the mixture. The amount of pure salt coming from this first 6% solution, we already found that to be 0.6 milliliters of that pure salt. How much pure salt is coming from the second 20% solution? Well, we can find that by multiplying. The expression is actually right here in the table, right? The amount of pure salt is just 0.20 times X. So we multiply 0.20 times 18. And what is that equal to? It looks like that is 3.6 milliliters. And that kind of makes sense that it should be more than 0.6 than the first solution because it's more concentrated and we're using more of it. So 3.6 milliliters of pure salt is coming in from the second mixture. And so that gives us a total of, if we add those two up, that gives us a total of 4.2 milliliters of pure salt inside of this 4.2 milliliters of pure salt inside of the 28 milliliters of mixture. And so if we want to get the concentration right now, let's assume we don't know what it is. We know we wanted it to be 15%, but is this actually a 15% concentration? Well, let's check. 4.2 divided by 28. And actually I have a calculator here. I'll just use a calculator. We could do this without a calculator, but we divide, and in my calculator I get 0.15. This is a 15% solution. So if you do mix 18 milliliters of 20% with 10 milliliters of 6%, you get 28 milliliters of 15% solution. We just wanted to make sure that we got a 15% solution. That is what results from this mixture. So good. That's what we wanted. All right. So that will be very similar to the problem that we had on worksheet number 1, that word problem, part B. Part A, you can get a little bit of help from, this statement here. For something that is sold by the pound, the dollar value is equal to the number of pounds multiplied by the price per pound. So notice it, dollar value, number of pounds, price per pound. Those are going, if you're going to use a table, those are going to be the 3 things in the column. And then, in the categories, well, it's whatever you're selling, walnuts, peanuts, cashews, or whatever's in the problem. Pecans, make a table, try to fill in what you know, and then use a similar reasoning as what we did here in this mixture problem to get the solution for part A. All right, part B, excuse me, is very similar. Oh, actually, oh, wait a minute. Yes, part B is actually very, very similar to the one that I did. Yeah, so, okay, well, that's okay. Uh, that's funny. I found mine in a textbook, in the textbook for our class. Um, didn't see that it was that similar. Okay, so but using a fresh mind, maybe get away from this for a little while, and then try it yourself without looking at the solution that I came up with, and see if you can get a solution for a problem in the worksheet. All right, that's it for this video. Hopefully that cleared something up. All right, see you in the next one.